Good evening, everyone. So today is our sixth lecture of for the course Introduction to Algebraic Geometry and Commutative Algebra by Dr. Dilip Patil. And in week number 6, we will discuss about ring of fractions and localization. So this is some preliminaries given. You can see that your A be a commutative ring, and for a multiplicatively closed set, this means that if uh, A comma B belongs to S, this should imply AB belongs to S. And let A to S inverse A be the inclusion map, and the first you have to show that S inverse A is a module, or let it be a ring with a natural ring homomorphism, and with this S inverse A is endowed with A algebra structure with the structure homomorphism. Yes, A algebra means that with this map they would B1 by B2. If this is your product, then this product is defined as IS of A of B1 by B2. So since S inverse A is a ring, so it would be product of two elements, and it would be ISA, that is A by 1. So let me just use as A by 1, AB1 by B2. Okay. Now we come to our first exercise. So the first exercise says that let A not equals to 0 be a commutative ring, and S0 it would be NZD of A, that is A minus ZA, and which is the set of all non-zero divisors in A. The ring of fractions QA is defined as S0 inverse of A. So non-zero divisors means that A dot B cannot be 0. Their product should be always non-zero. And the ring of you have to check that this is a multiplicatively closed set, that I will be not checking. And this says that the ring of fractions QA S0 inverse A is the total quotient ring of A with natural homomorphism A going to Q of A. In particular, it says that if A is an integral domain, then QA is the field of fractions of A. So if A is an integral domain, you can see that ZA is only 0. Therefore, this NZD of A is A minus 0. Like for Z, you will see that the NZD of Z would be Z minus 0. Z means the integers, and the Q of Z would be the rational numbers. So it is called the field of fractions of A. The definition is coming from there. Now we have to, first exercise is to show that S0 is the largest multiplicatively closed subset of A, for which IS0 A going to S0 inverse A is injective. Now recall that for any multiplicatively closed set S of A, car of IS equals to those elements from capital A such that there exists small s from capital S such that SA equals to 0. That is clear, right? And the injectivity of IS0, if you check that if you take small s from capital S0 and SA equals to 0, then since S is a non-zero divisor, we get A equals to 0, and therefore car of IS0 equals to 0, and therefore it is injective. And for the maximality thing, let us assume that let S be multiplicatively closed set with IS injective, and take any small s from capital S, and suppose s of a equals to 0, and then you will see that is of a, that is a by I, equals to 0 by I equals to 0, and in S inverse A, this would imply that uh, yeah, I mean, if is injective, then you would see that uh, this map would take to 0, and injectivity of is, this would force that a equals to 0, and so s is a non-zero divisor, right? Because if you take s as arbitrary, so therefore small s belongs to s, capital S0, and capital S belongs to um, capital S0. Now we have to show that every element in QA is either zero divisor or a unit. So your this field of fractions which we are seeing, we have to show that it is every element in QA is either a zero divisor or a unit. Now for the first thing, let's take a by s from QA with a belongs to a and small s belongs to S0, and for the case 1, let a belongs to S0, then a is a non-zero divisor, and so s by a is well defined, and a by s into s by a equals to s by sa, which is 1, therefore a by s is unit. So what you see is that if you take any element, if you take both the element from S0, then the fraction becomes a unit. Now if you take a from z of a, that is the zero divisor, then there would exist b by b not equal 0, such that ab equals to 0, and since is0 is injective, it would have to be b by 1 not equals to 0 in QA, and so that would imply that a by s dot b by 1 would be a by s, and it would be 0. So hence a by s would be a zero divisor in QA. Now every non-zero ring of fractions S inverse every non-zero ring of fractions S inverse of an integral domain A is an canonically isomorphic to a subring of the quotient field QA of A. So what we have to show is that there would be an injective map from S inverse A to Q of A. But this follows, right? Because since S0 is the largest multiplicatively closed set, so any closed subset of any multiplicatively closed subset is contained in this. Therefore, the S inverse A would simply be injective to S0 inverse A, but you have to prove this formally. So let A be an integral domain, then S0 is A minus 0 as we talked earlier, and QA is the field of fractions of A. Let S be a multiplicatively closed set with S inverse of A not equals to 0. So 0 does not belong to S. Now since A is an integral domain, every element of S is a non-zero divisor, right? Hence capital S belongs to is a subset of S0. Now define the canonical map to be from S inverse A to QA as A by S going to as it is A by S. Now viewing small s belongs to capital S and which is contained in S0, this is a well-defined ring homomorphism by the universal property of localization, right? Now for injectivity, suppose A by S is 0 in QA, and so there exists T of S0 such that T equals to 0, and since A is an integral domain and T not equals to 0, this would imply that A equals to 0, and therefore A by S equals to 0 in S inverse A. Hence phi is a injective ring homomorphism, so S inverse A is isomorphic to phi of S inverse A, which belongs to Q inverse A, Q of A. Now we go to our Next problem that says that for every ring A in which every non-unit is a zero divisor, now let us say the question one more time. For every ring A in which every non-unit is a zero divisor, the natural homomorphism IS0 from A to S0 inverse A is bijective. The hypothesis states that A, which equals to A cross union Z of A, which is both of them are disjoint sets, and equivalently every non-zero divisor is a unit, that is S0 is contained in A cross, A prefix cross. So for injectivity you can clearly check part A, which is says that S0 is the largest multiplicatively closed set, and A to S0 inverse A is an injective map. And for the surjectivity, suppose that every element of QA has of the form A by S, with A belongs to A and small s belongs to S0 of A cross. Since S is a unit, we have A by S equals to A is inverse dot S by 1 dot S, which is A inverse by 1, which is IS0 of A is inverse. Since IS0 is surjective and therefore bijective, we have this bijection among them. Now let us focus on the next problem. So let A be an integral domain and S0 be the set A minus 0, and K equals to S0 inverse A, which is the quotient field of A with natural map from A to K, as A goes to A by 1. We use throughout that S0 inverse K equal S homomorphic to K, and since every S of S0 is already a unit in K, and we have that S0 inverse of A equals to K. Now we have to show that A equals to K if and only if the canonical homomorphism phi from S0 inverse of home ring between K and A goes to home ring between or you can say module homomorphism from K to K over K is surjective. So try to do this for 5 minutes, then we will discuss. Okay, so let us start solving this. So yeah, K is your quotient field of A and A is your integral domain, and yeah, so you have to show that A equals to K. That means A is quotient field of itself if and only if the canonical homomorphism A0 inverse of this hom K over A is to hom K of K comma K is surjective. Now the map phi sends F by S to K going F K by S, and this is clear, right? Because F is a map from K to A and S is an element of S0. So K going F K by S, so F of K belongs to A, and A is a subset of K, so therefore F of K by S as an element of K is well defined, and yeah, so and moreover F from K to A is A linear and small s belongs to capital S0. Now let us assume that A equals to K, then S0 is A star, that means A minus 0, so every element of S0 is already a unit in A, and for any A module M, the canonical map F from S0 inverse M is an isomorphism, hence this is an isomorphism. Since A0 is a unit, for A belongs to S0, 1 by A belongs to A. Therefore, S0 also you can say. And therefore, it is easy to find a inverse map from S0 inverse M to M, and you can prove this. Suppose phi is surjective, and because identity map from K to K, there exists an A module homomorphism from F K to A, and small s belong to S0 with phi of F by S equals to identity of K. That is F of K equals to Sk for all small k belongs to capital K. And since Fk belongs to A, for every small k belongs to capital K, star gives Sk to F for all small k belongs to capital K. And set k equals to 1 by A square belongs to K, and f of 1 by A square equals to S dot 1 by A square, and which is equals to 1 by S of A. And hence S inverse equals to 1 by S, which belongs to A, and so S is a unit on A. And for step 2, if you see for any small b belongs to S0, the set if you take K as 1 by B, then f of 1 by B is S by B, which belongs to A. And step 3, take any A by B belongs to capital K with A belongs to small a belongs to capital A and small b belongs to S0. From steps 1, 2 and both 1 by S and S by B lie in A. So 1 by B equals to S by B dot 1 by S belongs to capital A. And therefore A by B equals to A dot 1 by B, which belongs to capital A, and hence capital K belongs to capital N, and since A is a subset of K, always A equals to K. Now, now we go to our next problem that says that let A be a commutative ring and capital S of A is multiplicatively closed. If S inverse A is finite A module, then S inverse of A is isomorphic to A by car of IS as A modules. Now by the first homomorphism, okay, you can try this for 5 minutes, then we can start. Okay, so let us focus on problem B, that says that let A be a commutative ring and H be a multiplicatively closed set. If S inverse A is a finite A module, then S inverse A is isomorphic to A by car of IS as A modules. So that means we have to show that the module map from A to S inverse A is surjective. Yeah. By first isomorphism theorem, there is a canonical injective A module map from A by car IS to S inverse A. So therefore, we have to show that I bar is surjective and that is IS itself is surjective. Now let A1 by S1 up to AN by Sn be a finite generating set of S inverse A as an A module with AI belongs to capital A and small si belongs to capital S, and set your small s as S1 S2 up to Sn belong to capital S, which belongs to S since S is multiplicatively closed. Now the key step is to note that for each generator using S equals to Si dot the product of Sj where j not belongs to I, S dot ai by Si equals to Sai by Si, which after a fairly simple calculation you can see that it should be Is of this, which belongs to Is of A. Now since the generators all satisfy S dot ai by Si belongs to Is of A, we obtain S dot S inverse A is a subset of Is of A. Since S by I1 is S inverse A is a unit, so multiplication by small s is an automorphism of S inverse A, and S inverse of A equals to S by 1 dot S inverse of A equals small s of capital S inverse A, which is a subset of Is of A. Hence Is is surjective and S inverse A equals to A by car Is. Now here is problem 6.6, which says that let A be a commutative ring and S is a multiplicatively closed subset, and pi by a map, surjective map from A to A by small a, the natural quotient map from for an ideal A of A. Try to prove the first problem that says that S inverse commutes with the nil radical. Nil of S inverse A equals to S inverse of nil A. Okay, so let us start solving the exercise 6.6 and we'll show that S inverse commutes with the nil radical. Nil of S inverse A equals to S inverse of nil A. Now for one part, let A by S belongs to S inverse of nil A, and so A belongs to nil A, and that is A to the power n equals to 0 for some n greater than equals to 1. Then A by S of n to the power n is A to the power n by S by n, S to the power n, that is 0 by S to the power n equals to 0 in S inverse A. So A by S belongs to nil of S inverse A. Now for the other containment part, let A by S belongs to nil of S inverse A, and so A by S to the power n is A to the power n by S to the power n equals to 0 in S inverse A for some n greater than equals to 1. By definition of S inverse A, there exists small t of capital A such that t dot A to the power n equals to 0 in capital A, and we compute that ta of to the power n equals to t to the power n a to the power n equals to t to the power n minus 1 of t dot A to the power n equals to 0. So ta belongs to nil rad of A, and since ts belongs to capital S, we can write A by S equals to ta by ts, which belongs to S inverse of nil radical of A. Therefore, the proof is complete. The second part, a prime ideal P of spec A is minimal if and only spec AP is singleton. That means there is exactly one element. So you can just try to prove this, then we will discuss. Okay, so let us start solving this. The prime ideal small p of spec A is minimal if and only if spec AP is singleton. Set capital A is to be A minus P. So AP is S inverse A. The standard bijection between spec AP and primes of A not meeting A reads as spec AP it has 1 correspondence with Q of spec A such that Q inverse S is empty. Q intersection S is empty, which equals to Q of spec A, where Q belongs to P. Since P itself always belongs to the right hand set, spec of AP is a singleton if and only if P is the only prime of A contained in small p, which is exactly the condition that P is the minimal prime of capital A. Now, for question C says that if A is reduced and small p belongs to spec A is minimal, then AP is a field. AP is a local ring with maximal ideal small p into capital AP. Now we have to show that AP is reduced. Since A is reduced, a nil radical of A is 0, and by part A, nil radical of AP is S inverse of nil A, which is 0 itself, so AP is reduced. Now for step 2, we have to show that PAP is 0. By part B, spec AP equals to P of AP. And since the nil radical equals the intersection of all primes, nil AP is P of AP. Combining with step 1 gives P of AP equals to 0. So therefore, AP is a local ring whose unique maximal ideal is 0, therefore AP is a field. Now we prove the question D, which has 2 parts, says that let A be an ideal of A and SA is 1 plus A. That is it is a multiplicatively closed set. We have to show that SA is multiplicatively closed, and A of SA inverse capital A belongs to M of SA inverse A. So therefore we have to prove this. So which is Jacob's radical of SA inverse of A. Okay, and we have to show the saturation. So I suggest you to try this for 5 minutes. Then we can start discussing this. Okay, so let us solve this. So yeah, so we have to show that SA is multiplicatively closed, but this is trivial, right? Because you can write 1 as 1 plus 0 of SA, so therefore 1 belongs to S of A, and for 1 plus A and 1 plus B from SA with AB belongs to A, we can write it as 1 plus A plus B of plus AB, which belongs to A, so it belongs to S of A. The product belongs to S of A, so SA is multiplicatively closed. Now A of SA inverse A belongs to M of SA inverse A, which is the Jacobson radical. In this case, we have to show that it is contained in there. Now it suffices to show that 1 minus x by s into y by 2 is a unit in SA inverse A for every x belongs to A and y belongs to A, and ST belongs to SA. Since ST belongs to SA, write ST as 1 plus A0 for some A0 of A, then 1 minus xy by ST equals to ST minus xy by ST, therefore which is equals to 1 plus A0 minus xy by ST. And since A0 minus xy belongs to A, the numerator 1 plus A0 minus xy belongs to SA, as both numerator and denominator lie in SA. This fraction is a unit in SA inverse A. And by the characterization of the Jacobson radical, every element of SA inverse A lies in J of SA inverse A. Now for the part 3, which is saturation, the saturation SA bar of SA bar is pi inverse of A by small a cross equals to F of A. A bar is a unit in A by A. By definition, SA bar is F of A, where A by 1 is a unit in SA inverse A, and F of SA bar is which implies F bar belongs to A by A cross, and if F by 1 is a unit in SA inverse A, there exists G by S with Fg by S is 1 in SA inverse A. This means there exists T of SA with T of Fg minus S equals to 0, and so Tfg equals to Ts, and since Ts belongs to SA, which is 1 plus A, we have Tfg congruent to 1 mod A, and since T congruent to 1 mod A as T belongs to 1 plus A, it follows that T bar equals to 1 in A by A, and hence Fg bar equals to 1 in A by A. So F bar G bar equals to 1, meaning F bar belongs to A mod A cross. Now you have to show the other part, that if F bar belongs to A mod A cross, we have to show that F belongs to SA bar. If F bar is a unit in A by A, there exists small g belongs to capital A with Fg congruent to 1 mod A, that is Fg equals to 1 plus A for some small a belongs to A, and that is Fg belongs to SA. If SA inverse A, this gives F by 1 into G by 1 equals to Fg by 1 in SA by 1, which is a unit. Hence F by 1 is a unit, and so F belongs to SA bar. Now for the next question, we show that let A be a commutative ring and small a belongs to capital A and ideal, and S belongs to A multiplicatively closed subset. Write S bar as pi A of S which belongs to A by A for the image of S under the residue map pi A, which is a map from A to A by A, and note that S bar is a multiplicatively closed since S is. We have to show that we have to construct the canonical map, so which is we can define phi from S inverse A to S bar inverse A by A mod A as A by S goes to A mod by S mod. And well definedness, for the well definedness part, you can see that 1 second. Yeah, So well definedness, if A is equals to A prime by S prime and S inverse A, then there exists T of capital S such that T of A is inverse minus A dot is equals to 0 in capital A, and applying phi A T bar as A bar S bar prime minus A bar prime minus A bar prime S bar equals to 0 in A mod A, with T bar belongs to S bar, so A bar by S bar equals to this A bar prime by S bar prime and S bar inverse A by A. And to check ring homomorphism, you can see that this you can check by yourself, that these are just fairly routine calculations, and this will be a algebra map because phi of is of A is phi of A by 1, which is A bar by 1 bar, which is is bar of A bar, which equals is bar of phi A evaluated at A. And surjectivity, every element of S bar inverse A by A has the form A bar by S bar for A belongs to A and the small s belongs to capital S, and phi of A by S equals to A bar by S bar. And car phi, we have to show that it is of the form A into S inverse A. A by S is car of phi if and only if A bar by S bar equals to 0 in S bar inverse A by A, which holds if and only if there exists T of capital S with T bar into A bar equals to T A bar equals to 0 in A by A, that is Ta belongs to A. We claim this is equivalent to A by S belongs to A of S inverse of A. If Ta belongs to A, for some T belongs to S, set small b equals to Ta belongs to A, then A by S equals to Ta by Ts equals to B by Ts with B belongs to A, and Ts belong to capital S, so A by S belongs to A of S inverse of A. And similarly you can check the converse direction also. Now for the step 3, the isomorphism by steps 1 and 2, and the first isomorphism theorem, phi descends to a canonically algebra isomorphism S inverse A by A of S inverse A, which belongs to S bar inverse A mod A equals to pi of S inverse A mod A. And the bijection on spectra, we establish that spec of S inverse A mod A, there is a map isomorphic to the collection of all P from spec A such that A belongs to P and S inverse P is phi, by composing two standard bijection. Bijection 1 says that the localization part, that the standard result for the localization gives spec of S bar inverse A mod A is isomorphic to the all Q bar from spec A mod A such that S bar intersection Q bar is phi, and the map goes like this: Q goes to small a bar from A mod A such that small a bar by 1 goes to Q, belongs to Q. And the bijection 2 is that the standard result for quotient gives spec of A mod A, which is isomorphic to the collection of all P from spec A such that A belongs to P. The Q bar belongs to P as pi A inverse Q bar. Compatibility of the S condition, which says that A prime Q bar belongs to spec of A mod A, satisfies S bar intersection Q bar equals to phi if and only if pi A of S intersection Q bar equals to phi, that is S intersection pi A inverse Q bar equals to S intersection P is phi. And composing these two bijections yields the explicit map Q belongs to Q goes to P equals to pi A of Is inverse Q, which is A of capital A bar by 1 belongs to Q, which is a bijection from spec of S inverse A by A onto P of spec A, and A belongs to P and S inverse S intersection P is phi. So these are the solutions for today. So I hope you understand this, and if not, please send me a mail, and in the next class will be week 7 and we will do some other problem. So if you need to mail, you can just send me on this. Okay. Okay. So uh, anyway, good night.